Hello, dear students. I am Samir Velankar. I welcome all of you to this second video on the topic AVL tree. In the previous video, we saw what do you mean by balanced binary search tree. When is the binary search tree balanced? And we saw an example where the binary search tree is balanced, and we saw an example where a binary search tree is not balanced. We also saw that to check whether the tree is balanced or not, you should check the nodes from the bottom level, and level by level you should go on the top and check the first node which is disobeying the rule. The rule was difference between left height and right height absolute value should be less than or equal to 1. Now in this video, what we will be learning is that there are four cases. We are going to learn four cases in which the binary search tree becomes unbalanced. Now, what are the reasons? What I am trying to explain is what are the reasons for a binary search tree to become unbalanced? And there are four reasons why the tree becomes unbalanced. And because there are four cases, to solve these four cases, there are four rotation algorithms. And these rotation algorithms were created by AVL, Edelston, Belsky, and Landis. It is unbelievable that these four rotations algorithms are so simple that very easily an unbalanced tree, the tree which is unbalanced, can be transformed into a balanced tree. Let us see what are those four cases. Now, case one in which the tree becomes unbalanced is left-left case. Just imagine that we have a tree like this. What it means is we inserted 10 first, then we inserted 5. So 5 will go to the left of 10, and then we inserted 2. So 2 will go to the left of 5, isn't it? But now you notice what will happen, after inserting 2. Just now we inserted 2, imagine, this tree has become unbalanced. Because if you notice from bottom level, remember you have to check for balancing factor from bottom level, you can see that 2 is balanced. Because left height is 0 and right height is 0. So the difference is 0. 5 is balanced. We are going one level up now. So left height of 5 is 1 and right height is 0, difference is 1. But the node which is storing 10, that is, you can say it is root node, is not balanced. But the left height of 10 is 2 and right height is 0. So 2 minus 0, difference is 2, which is not allowed, and 10 is not balanced. So this tree is not balanced because 10 is not balanced. Again, you watch, it is so important that while checking for balancing factors, you have to check from the bottommost level and find out the first node which spoils this rule from the bottom up. From bottom up, you have to check. So, from bottom, the first node which spoils the rule is node 10. Now, which case is this? This is easily left case. I mean, why is 10 not balanced? Check it. Why is this node 10 not balanced? 10 is not balanced because 10 is having a left child, which is again having a left child, isn't it? That is left. For some time, you imagine that the node which is storing 2 is not there in the tree. Just imagine node 2 is not there. Then we will have a tree which stores 10, and to the left of 10 we have 5. Imagine 2 is not there. Then 5 is balanced, 0 minus 0. 10 is balanced, 1 minus 0. So the tree is balanced in that case. So the point is, why is 10 not balanced? Because 10 is having a left child, which is again having a left child. I hope you understand. And the left height of 10 and right height of 10, the differences is greater than 1. Therefore, 10 is not balanced. and the case is known as left-left case. I hope you have understood why the case is known as left. So definitely this tree is not balanced. Now, how do you balance it? Now, AVL, Adelson, Welsky, and Landis gave a simple rotation algorithm. What they say is that you know that 10 is not balanced. Then simply rotate this 10. This 10 you rotate to the right of 5. See, right of 5 is null, isn't it? It is empty. So simply take this 10 and say 10, you should not be parent now. 10, you better become right child of 5. So you can imagine that 5 now has right child as 10, isn't it? See how this 10 actually was the parent, and now this 10 has been rotated to the right of 5. This is called right rotation. This is this right rotation. Yes, exactly, because 10 was rotated to the right of 5, isn't it? So now 5 has right child 10. And by the way, what was the left child of 5? Left child of 5 was 2 and it will remain 2. Observe the previous tree. And this is the new tree that we have. 2 and 10 now are leaf. 5 becomes the parent. Now, give your comment on this tree. This is balanced. Come on, no need of proving it. This is balanced. And also, it is a binary search tree. Remember, we need a binary search tree. So, less than and greater than rules are also preserved. So, I hope you know how to settle the case left left case. If the tree becomes unbalanced due to left left case, then you simply do right rotation. And which node do you rotate right? You rotate that node to the right, which is not balanced. So you understand that 10 was not balanced. So 10 was rotated to the right. Right of whom? 10 was rotated to the right of child of 10, left child of 10. Left child of 10 was 5. So 10 was rotated to the right of its left child, isn't it? All right. Let's see the second case now. Now the second case is right case. You won't take time now to understand this. Suppose we have 10 and we have added 20. So 20 will go to the right and we have added 30. 30 will also go to the right of 20. Now you can easily see from the bottom up, from the bottom up, 30 is balanced, 20 is balanced because left height is 1 and right height is 0. Left height is 0. I'm so sorry. Left height is 0 and right height is 1. So the difference is 1. Whereas 10, if you observe this 10, left height is 0 but right height is 2. So 10 is not balanced because difference of left and right is greater than 1. But the case you observe, 10 is not balanced. 10 is not balanced because it is having right child, which is again having right child. So this is right case. And to handle this, AVL gave left rotation. Just rotate this 10 to the left of 20. Observe. Rotate 10 to the left of 20. So the tree that we will get is 20 will take up a place such that 20's left is going to be 10. And what was 20 is right in the earlier tree, it was 30. That will remain 30. It's not going to change. So 10 and 30 are now leaf nodes, and 20 being the parent. Now observe the tree that we have drawn is indeed balanced, no need of proving. So easily, if you have right case, then you just do left rotation. This is called left rotation. Now let's come to the third case, left right. Many authors call it as zigzag case also, left right. And left and right case are known as zig case. Okay. When you will get left right case, if you have 10 and then you add 5, so 5 will go to the left of 10 and then you add, let's say, 8. Now you watch, this tree is also not balanced. Yes, the tree is not balanced. due to 10. Because if you check from bottom up, 8 is balanced. Bottommost level 8 is balanced, 0 minus 0. Next level up, 5 is balanced because left height of 5 is 0 and right height of 0 minus 1, difference is 1, which is allowed. But 10 is not balanced, isn't it? Because left height of 10, observe, left height of 10 is 2. You can see that there are two levels down here, and right height of 10 is 0. So 2 minus 0, 2 not allowed. Difference of is not allowed. Now, why is 10 not balanced? Is because 10 is not balanced because of left right case. 10 has a left child, and that left child has a right child, isn't it? So, how do you handle this case? Now, to handle this case, what you do is you just check left child and left child has a right child 8. Then that right child 8 is simply put at the node which is not balanced. 2 is not balanced in this example, 10 is not balanced. So simply put that 8 at the place of 10. Okay, come again, 10 was not balanced due to case left right. Then whoever is that right child, that is 8, is simply put at the place of 10. Now you only tell me if 8 goes as the parent, then left of 8 will remain 5, isn't it? But where will 10 go? Because 8 has occupied the place of 10. 10 will go to the right of 8 because 10 is larger than 8. And this is the tree we get. This is the tree. You can watch that tree is, of course, balanced. Isn't it so? Just check it out again. Just check the left right case. Suppose we have, oh, I'm so sorry for this. Suppose we have a node which stores 20, left of 20 is 10, and right of 20, let's say, right of 20 is 50. Know that 20 is not balanced due to left right case. Then simply put 15 at the place of 20. Now, if 15 goes at the place of 20, then where will 20 go? 20 must go to the right of 15 because it is larger than 15. The left child of 15 will remain 10. 10 was already left child of 20. It remains as left child. So we have got two leaves, 10 and 20, and 15 being the parent. This is of course balanced. This is balanced tree. So how do you handle the fourth and the last case, right left? This is very easy for you now. Suppose you have 10, to the right of 10 you have 20, and to the left of 20 you have 15. Observe again that this binary search tree is not balanced because 10 spoils the show. 10 is the first node from the bottom whose left height is 0, whereas right height, you observe the right height here, right height is 2. 0 minus 2, difference is 2, which is not allowed. And the case is left, right, left case. How do you handle it? Is that this 15 is simply put at the place of 10. Now, if 15 takes up the place of 10, then where will 10 go? Because we have overwritten 15 at the place of 10, but 10 is smaller than 15. So 10 is going to take left child of 15. Notice the 20, the value 20 has to go to the right of 15 because it is larger than 15. Now we have two leaf nodes. 10 and 20 are leaf nodes and 15 being the parent. This tree is of course balanced. So these four cases, left left, right right, and right left, are the cases in which the tree becomes unbalanced, and we can easily balance the tree by using rotation algorithms. In the next video, in detail, we will be learning how to construct AVL tree from the scratch, and we will be taking data from 1 to 7. Did you observe one thing that your teacher has not yet explained to you, that why we should balance the binary search tree? and what is so bad about unbalancing. So, one paragraph over here in the slides was left out by your teacher. The paragraph was about performance of a simple binary search tree over AVL tree. Why I am telling you is this is because if you learn good pages, web pages like Wikipedia and others, you will see on the very first page they will explain importance of balancing. What is so nice if the tree is balanced? Well, we are coming to these facts, and the words like the time complexity and all that is going to be explained by your teacher, but you will have to wait for one or two videos. See you in the next video. Thank you very much.